Well, here's our first point of concurrency, and we're going to illustrate it with a random triangle. I've got a random triangle ABC right here, and I'm going to start by putting in, well, say a perpendicular bisector. There's one perpendicular bisector, there's another. And as we all know, a triangle has three perpendicular bisectors right there. And what do you know? They all meet at a common point. That's, well, there's a vocab word for us. That is a point of concurrency. It's one of the four that we're going to study. This one is called the circumcenter, the intersection of the three perpendicular bisectors of a triangle. So these three green are perpendicular bisectors. Point P is the circumcenter. And what that means, simply put, it's the center of that circle which contains the three vertices. And you can play with this and you'll notice a couple things. Here P is on the inside. We could shade the figure if that helps. It's on the interior of the triangle. And let me move it like this. Here it's on the triangle, or on one of the sides. And here it's outside the triangle. So this point can be outside, and you'll notice the different types of triangles. Obtuse, right, and acute. So there you go. This is the circumcenter. Oh, let me just show you these three segments. Of course, your book likes to fuss about this, and you'll see the drawing oftentimes here. These are simply the radii to that circle, which means, of course, P, or the circumcenter, is equidistant from the three vertices of the triangle. And that's it. Oh, so many numbers in this diagram. Let's not get confused. We're looking for BG. And all these blue segments are perpendicular bisectors. We're used to seeing the whole line, the perpendicular bisectors. Now they're confusing us with segments. But in any event, they meet at this point G. This point G is called the circumcenter of the triangle. Remember what that means. If you remember, that means the center of the circle passing through these three vertices. Well, that means all these must be the same. And after all, that's what this other definition, point G, the circumcenter, is equidistant from the three vertices of the triangle. After all, they're all radii of the same circle, and of course then BG must be 9. Just like that. Well, this is similar to the last exercise, except this triangle has its point G, which is the intersection of the perpendicular bisectors, all in blue here, external or outside of the triangle. Of course, that's going to be true in the case of an obtuse triangle. So this is all you need to know. Again, G is the circumcenter. So that makes all those red radii. And GA, that is, must be 11. Well, here we go with a random right triangle. And, well, we've got it all sketched out here. And let's demonstrate what a construction would look like. So I'm going to simulate the compass swings. Let's say I'm perpendicular bisector here. I would say the swings would look like this. You know, the needle there swinging through here would give me this arc. You can see that. Needle here swinging through this point would give me these arcs. And of course, that would give me one of the three perpendicular bisectors. And these would be the compass swings for this side. And I can visualize that one right there. And of course, for the final side, third side, the hypotenuse, I'll swing the arcs out there. And there's my line. And we were asked to do a right triangle. Obvious reasons. We want to see this. In this case, the circumcenter in the right triangle is on the hypotenuse. And more specifically, it's actually on the midpoint of the hypotenuse. And we'll learn a lot of really neat stuff about that in the section about, well, when we get to arcs and circles, and I guess even right triangles. So there you go. Circumcenter is the midpoint of the hypotenuse in a right triangle. Well, here we go. 3 questions, 1 diagram. So I've got this arbitrary triangle here with the 3 perpendicular bisectors meeting at the circumcenter. You're going to have to trust me as I didn't put in all those fancy tick marks. So here we go with 20. The circumcenter, which you can see there, of a scaling triangle is inside the triangle. Well, it is right now, but now it's on the triangle, and watch this. And now, oh, it's outside. Yeah, this scaling triangle happens to be obtuse. So it might be on the inside, might not. So that's going to get a definite sometimes. Okay. Let's go to 21. If the perpendicular bisector of one side of the triangle passes through a vertex. Well, wait a minute. Then by definition, we just learned that, then these 2 points, or these 2 segments, must be congruent because any point on the perpendicular bisector is equidistant from the endpoints of a segment. Whether it's that one, or as you can see right here, or whether it's this vertex, it doesn't matter. Right now, these 2 must be the same. And I suppose, okay, let's go for the trifecta. If I put this one here, now these 2 must be the same. So that's our theorem. Oh, what number was that? 5.3, our converse of the perpendicular bisector theorem. So that is going to be a solid always. So again, if it passes through like that, that triangle's isosceles. So 22, our final. Perpendicular bisectors of a triangle intersect at a point that is, wow, equidistant from the midpoints of the sides. I think I know what they're getting at. Let me draw you this picture. If I could put this triangle, this circle, so it's just tangent, like this. Ooh. Oh, very nice. Well, very close. And what we're approaching is, of course, an equilateral triangle. In the case of an equilateral triangle, this circle demonstrates that not only will the distance to the vertices be congruent, but the distances to the sides as well. Because after all, these short distances, the distance is to the side is the perpendicular distance, and if they're all the same, that would mean this circle would fit exactly inside it. So that's going to get a solid sometimes, which means in the case of an equilateral triangle. Oh, finally a dog walking problem. Nani likes those. So we've got these 1, 2, 3 places, and we're assuming there's no obstructions. You don't have to walk around curbs or buildings or someone else's yard, of course. And we're just going to find the point that's equidistant between the 3. And wouldn't you know it, that's exactly what we've been doing this chapter. I'm going to make a little triangle between the 3 locations. If I were to construct the 3 perpendicular bisectors, I would reach a magic point. And this is the magic point we know as the circumcenter because it is equidistant from the 3 vertices of the triangle. So I'll move that construction out of the way, and that's the magic point right there. So there you go, math to the rescue again. Well, here's a great opportunity for a coordinate proof. I'm starting with this arbitrary right triangle, which we have positioned very conveniently in the first quadrant of the coordinate plane with one vertex, the right angle at 0, 0, because of course the x and the y-axis are perpendicular, forming right angles. That's going to come in handy. And I've assigned the variables, well, let's say the for A and B, the coordinate values, the values for this variable coordinates. That's the word I'm looking for. And B is, again, as you can see, 2h, 0. You'll see why in a minute. Well, of course it is. So this is our given, the diagram. Because we need midpoints, first thing. Well, that's why we arbitrarily chose 2h, so the midpoint would be h0. And of course, over here, 0k. And this would be hk. 1h, 1k. Well, if you all agree those are the midpoints, then all we've got to do is let's construct some perpendicular bisectors. Now, I just named them J, K, and M to make it easier, J, M, and K. Because when I look at this one, perpendicular bisector J, it goes through the midpoint S, so there's the bisector. Perpendicular, well, it must be horizontal because it's perpendicular to a vertical line. If it's horizontal, I know that it has a slope of 0 or a constant y. It must pass through this point, hk. After all, it's here on 0k. Now the same argument can be made for M, except it is perpendicular to a horizontal line. So it is a vertical line. Vertical line has a constant, oh wait for it, abscissa. That's right, that's the x part there. T is h0, v is hk. So what we know, since vertical and horizontal lines are perpendicular, we've just demonstrated these two pass through point V. Now, of course, H passes through point V because it's just plain the perpendicular bisector of AB, so it has to go through the midpoint. So all three of them are concurrent at point V. Now, that should be sufficient right there, and I could say, ta-da, it is the circumcenter of this figure. But wait, there's more. We could, well, I suppose if we wanted to, we're going to say, of course, V in this case is the midpoint of the hypotenuse. That's the point that's going to work for all right triangles. And if we wanted to really dazzle everyone, we could do this. We could pull up a little distance formula and we could check it out here. And the distance, for example, from C to V is, of course, well, you got it right there. I mean, you've got a rise and you've got a delta x of h. Well, that's confusing. A delta y of k. So the square root of h squared plus k squared, and you can see that no matter which of these three measurements you're talking about. So I think we're done.